Hello, I'm Doug Walker. I'm with the Global Network of Astronomical Telescopes. We're a nonprofit group with folks working on our project from different parts of the world. So what we want to talk about today is we're going to give you an example of a active galactic nuclei quasi-stellar object that we found in our MOTES NAT sky surveys. I want to explain all those acronyms in just a minute. So before I get started, I just wanted to say a word about this presentation is dedicated to our recent lost friend and colleague, Roy Tucker, who passed away just a few months ago. Roy Tucker was essentially the genesis behind the MOTES system. It was designed for discovery of asteroids, near-Earth asteroids, and he had, during the late 90s and early 2000s, using his system, he had over 700 asteroid discoveries to his name, so he was quite prolific in that field. And it's his system that all this work is based on, and we will miss him dearly. So, okay, so what we're going to talk about today as we work through this presentation, first going to talk a little bit about what the objective of this study was, why we're doing it, give you some information about the observations we actually used from the MOTES system to do our initial analysis. We're going to tell you about how we found the object of interest. Okay, we did a correlation between our MG survey data and some published catalog data, so I'll describe that. So once we had our object of interest and did our initial analysis from our surveys themselves, we first went through a variance analysis on the photometry of the data, because we really wanted to understand just what we were seeing, because these things are very faint. I'll give you the details in just a minute. What we were seeing was actually a variability in the target of interest versus atmospheric distortion in that case there. So we did that, and then next stage we went through is we did a variability analysis of seeing if the object was actually varying in magnitude over time, and so I'll tell you about that. And then one of our colleagues, Andy out of Australia, followed up with a short-term analysis, or observations and analysis on the target of interest. And we did that basically to demonstrate that we can take small telescope systems, follow up these targets, and actually get some useful data out of that. And then I'll conclude everything and wrap it up. All right, so this came out of our study here came out of a NAT science meeting in August of last year. And so basically what we have is that there's this moving object and transit event search system, the MOTES system, as I described, was developed for asteroid detection and discovery. As a set of three 14-inch Newtonian telescopes set up. And so we've had, in addition to the discovery of the asteroids over time from that system, we have years worth of survey data, and we've done some work in long-term variable stars in the system itself. And so during the science meeting last August, we were discussing, is there other objects of interest in our data sets that we could potentially mine? So that's the genesis of this study here. So what we wanted to do is we conducted, and this is just an initial investigation into the optical variability of the known quasi-stellar objects, quasars themselves. So the objects have to lie within the celestial equator, 0 plus degrees declination. The survey bands, they all have to be within that range there, and I'll give you some more information on that in just a second. Okay, so our basic approach was that we have our MG catalogs, okay, survey data, and here I'm calling it MG1 through MG6, and I'll talk about that in just a second. So we have two sets of catalog data in a particular declination band. So what we did, we took the Million Quasars, milliquads catalog version, online version. We did a correlation, just basically a cross correlation between what we could see in our survey data and the catalog data and came up with a list of potential targets. So from there, we ran it through a NAT data pipeline. Okay, so we took the catalog data, took out the FITS images using the Rada-Simpson declination, pinpoint the FITS images that we had where the target should be, run that through our NAT data pipeline, which has been recently updated and developed. And that you can get more information from that by here in the Symposium presentation given by Crane and Associates there. So that runs through the NAT data pipeline, and what comes out is a series of images that we can then go do photometry on and produce statistical analysis of the target of interest. So the observation data itself comes from MG1 or MG6, which are the names of our survey catalogs. So there have been 7 MG surveys that have been completed. The 8th one is currently underway. Each one is a duration of about 2 to 3 years. Okay, it covers about 48 arc minutes wide section of the sky at whatever declination we're pointing at. So each different surveys are pointed at different declinations. So for this case here, 1 and 6 was covering the same strip of sky, and that's why we're using those 2 sections of survey data for analysis here. So even though our telescopes are open filtered, limiting magnitude is about 18 or 19th magnitude, and that's due to the integration times, which is about 3 minutes, and that's due to the rotation of the Earth across the celestial sphere there. So, and again, you can go get more information from that from the paper and presentation by Crane, so and his colleagues. So the data reduction pipeline is we applied that to all the MG surveys. Each one produces a relational database, which then we can go in there and pick the objects of interest out of that relational database. So the survey correlation, okay, again, MG1 and MG6. Again, we crossed it with the Billy Quad's catalog, and what we did, it was a positional relationship match. So initial search produced about 290 positional matches within about 5 arc seconds of the targeted coordinates coming out of the Millimax catalog. Objects of interest that we were going to go study had to be detected in both MG1 and MG6 surveys. Now, this chart here is showing you that the majority of the cataloged quasi-stellar objects are really fainter than, majority of them are fainter than what we can detect and how deep we can go with our NAT system, the NAT telescope MOTEST system here. So as you can see, the overlap here from about 17 to 18 or 19, this little region here is really where we overlap with the catalog for potential targets of interest. So we found multiple targets. We chose one for this initial study, and that is cross-referenced to the WISEA calibration name here, and I'm just calling it for this talk here as our target QSO. We actually have another name. We've identified this in the paper, but instead of rattling that name off for the whole talk, I'm just calling it the target QSO. A finder chart down here will show you, which I'm pointing to, will show you the actual QSO position. Here's a reference star, and then here's a check star. We've used multiple check stars in their photometry analysis against a QSO. So I'll explain that in a minute. So over here on the right, showing you data from the, this is the NARU, this is the very large array sky survey, flux images, density images at 1.4 gigahertz. So we have a very strong radio source that corresponds to the QSO. We know that quasars are very strong radio sources. That's the way they were initially discovered. So. Okay, on to the photometry variance analysis. So we looked at comparing the magnitude of the target across 4 sets of observation periods, right? So this first set of observation period corresponds to the MG1 catalog. The second 2 sets of observation periods or series, as we call them in the paper, are from MG6. So MG1 over here, MG6 over here. So here we're showing you on the same, well, it basically have detrended the reference star, and this is the mean of the reference star, and the QSO is in referenced off, is in set off of that. So here's the name in the paper if you're interested: MG1, 122, 182, and it's in black. So that's our QSO object of interest. Here's a single check star. We've used multiple check stars. This is just an example of one. And so over here on the right, again, across the 4 observing seasons, I'm showing you the magnitude and standard deviation off the zero mean line of the check star and the QSO. And so you can see right here, the QSO has a much larger magnitude differential off the zero mean line than the check star does itself. So, and then last column is the standard deviations of those measurements. So that was just real quick summary of the photometry analysis. Now for the variability analysis, we look for longer term trends in the QSO behavior. So we found we can match what the data we had on top of other surveys out there. So here is an example of setting our MG survey data, which is blue here in this figure, against the Kettling the Sky survey in the red, and then the Zwicky Transit Facility survey over here in the black. So if we map those two, we see that we have a pretty good match here with our MG catalog survey data, especially with the Kettling the Sky survey. So we can combine these together. We've got a light curve with a span of about 19.7 years. So it's a long-term observation of this QSO. If we look here on the right, here's a phase diagram of this data here on the left. And this is a Fourier 2-term fitted model to the data itself. So you can see that it looks like there's some sinusoidal variability in here. Look at the period on this guy here is 2733 plus or minus 124 days. Okay. So not only did we look at that visually, we also ran some analysis programs trying to discover more accurate estimate of the period. So we ran the ANOVA analysis routine on the data itself. We came up with this chart on the right is showing you ANOVA, using Paranzo. We used a commercial package, Paranzo. Running ANOVA here is on the original data. And so we have a peak here about 2725, which corresponds pretty closely to the peak here of 2733. So we think we got a fairly good handle on the period of the object of interest. So the top panel here is just our data, and then we went through, we actually generated some synthetic data, and based on that curve, and we see we've got basically the peak at the same point. And then the panel C down here, it's the same thing. We did some additive noise with about 0.1 magnitude on there. So if you notice up here, we've got a cluster of peaks in here, about 300 to 900 days in this region. Okay, and then again, this peak is somewhere about 2743. Plus or minus about 119 days. So that's looking at the MG survey data. Okay, so the Colombgun Observatory in South Australia, Andy took his 14-inch scope down there, and with his 8300 camera on there, and we went and did short-term nightly observations and collection of data on our QSO target. And the purpose of this was to try to see, can we detect short-term variability in target by doing follow-up observations. So we've shown you that it looks like we can detect longer-term variability. So now we're looking at short-term variability. So here's a composite image here, co-added frames, and this is back on the 11th of March this year. And there's our target QSO at this point right here, where it points to, and the faintest stars in this image here are about 19th magnitude. All right, so Andy went through, he had 30 calibration stars around the target, okay, and he then took a fitted light curve of trying to look at the magnitude and determine what the magnitude of our target was versus on a magnitude differential calibrated curve, okay. So he took the data, he did a least squares fit, and came up with this calibration, magnitude difference calibration against the actual magnitude of the target itself, and to get a better handle on what the actual QSO magnitude was. Okay. Let's see if there's anything else I'm going to say about that. No, that's good. So, and then here's results across 10 consecutive nights, and measured in his 14-inch scope. Okay, so you can see here using those calibrated off the G passband what our best estimate what the error bars are for what the magnitude variation is going on with the QSO target itself. So based on this, and then Andy did an excellent job of doing the calibration. Based on this, it looks like there is some potential variability, short-term variability in this target that we can detect. All right, what's some conclusions here? We really believe that light curves made out of our MG data catalogs, we can go pull that data for objects brighter than about 17 or 18 magnitude. So we can perform analysis on those specific targets that meet that criteria. Long period variations of amplitudes about 4 magnitudes or greater are detectable. When I say long-term period variation, we're talking somewhere, 1,000 days or better, whatever. So the variation in the MG data can be enhanced by using other complementary observations from the other surveys, and we mentioned 2 here, Catalina Sky Survey again, and also the ZTF. So, and Andy has shown that high temporal frequency can be detected in some of these targets using small telescopes with the CCD cameras. So follow-up observations can be very useful in trying to get a handle on short-term variability. And then what we want to do for the future, so this again was an initial study, and so it looks like it is worthwhile to go investigate the database light curves for objects brighter than about 17.5, 18 magnitudes. And so the longer term goal would be to find targets with long period quasi-sinusoidal light curves, which then may be potential evidence of binary black holes. And so that's described more in the paper, that with potential stochastic systems that might also represent the behavior too. So, all right, I think that ends my talk, and thank you for your time, and enjoy your day.